So let's now relate the Poynting vector to the intensity of the electromagnetic wave. And the intensity is defined as the time average of the Poynting flux. And by the Poynting flux, I mean the magnitude of the Poynting vector. So it's the time average of the magnitude of the Poynting vector. So if you do the math and evaluate this intensity, which is something you're going to do yourself a little bit later, then what you find is that this intensity, if I take the solution to Maxwell's equations that we've derived that describes a propagating sinusoidal wave, sorry, propagating this way, and just do the math, what you'll find is that what you get is the magnitude of this electric field, which we've been calling E naught, the magnitude of the magnetic field, which we've been calling B naught, divide by the constant mu naught, and there's a 2 here, which you're going to have to derive a little bit later. It's actually where this 2 comes from. I'll just tell you at the hand waving level. This comes from the fact that if you average the square of a sinusoidal wave, you get 1/2 the peak value. That's where this 2 comes from, but you'll see it by actually following through the algebra at a later point. Other than the 2, this should be a straightforward formula for you to understand, because it's the same things that we have here. But now let's remember that in the electromagnetic wave solution that we found, the peak magnitude of the B is related to the peak magnitude of the E. They're proportional to each other, except with a factor of C. So I can write this also as E naught squared over 2 mu naught C. Or I can eliminate the E naught. I can take E naught and replace that by B naught times C, and this will then gives me C times B naught squared divided by 2 times mu naught. And what you see here is that the intensity, or the time average of the Poynting flux, is given by E naught B naught times a constant, or by E naught squared, or by B naught squared times a constant. And this should ring a bell, because remember that what E squared was the energy density of the electric field. And what B squared was the energy density of the magnetic field. So what this should make you think of is that as an electromagnetic wave is going through space this way, it has a certain intensity. That intensity is the amount of energy that it is carrying per unit cross-sectional area per unit time in this direction. And that is going to be related to the energy density of the electric and magnetic fields at one moment in time. So you can think of it as I have some energy density and it's moving, and that gives me an intensity or a flux.